So in this video we are going to cover the following topic. Amino acids are zwitterions. And zwitterions means that amino acids have a group that is positively charged and a group that can be negatively charged. So in order for us to see the equilibrium, we are going to use the simplest amino acid as an example. The simplest amino acid is glycine. That is abbreviated as GLY or just G, right? And it has the following structure. So we start with an amino group. We will start with the most protonated form, amino group, a hydrogen as a side chain, and carboxyl group in its protonated form. So the first deprotonation will be, of course, for the carboxyl group, because the pKa for the carboxyl group is around 2. So to be exact, it is 2.3 or 2.35, depending on the source that you have. So if you have a pH which is higher than 2.3, right, about 1 unit of pH higher, then you would have deprotonated carboxyl group. So we are going to write this equilibrium. You still have the amino group protonated, but the carboxyl group becomes deprotonated with a negative charge. And now, so of course that is a zwitterion form, right? So now if we start increasing pH even further, and the pKa for the amino group is around 8, 9, actually 9.6, right? Then you will start deprotonating the amino group, and the last form of glycine that we need to draw would be the one having both amino group and carboxyl group deprotonated. So here you can see how the charge of glycine switches from 1 plus to 0 to 1 minus, depending on the pH. So if we want to see actually the concentration of each form, how it depends on pH, we need to start with the titration curve. And the titration curve is the dependence of pH on the concentration of or amount of strong base added. So if we use sodium hydroxide or any other hydroxide as that strong base, we will have equivalence of that strong base as our x-axis. And the range for the x-axis will be from 0 to 2. Okay? And the good points, the valuable points here are when you add 0.5 equivalent of sodium hydroxide, 1 equivalent, and 1.5 and 2. So what happens, and let's see the range of the y-axis, right? So we'll have something like that. So we'll have 4 here, 1, 2, 3, 1, 2, and we'll have 4 here, 10. Okay, so what happens if you add 0.5 equivalents of sodium hydroxide? If we just, so we start with no sodium hydroxide, right, a very acidic pH here, so we're starting with that form. And this, if we start adding some sodium hydroxide, some molecules of the most protonated form of glycine start being deprotonated, right, with forming its conjugate base. So pretty much we are looking at this equilibrium right here that is characterized by the pKa of 2.3, and we need to remember the Henderson-Hasselbalch equation that relates the pH of the solution to the pKa and decimal logarithm of the ratio between the conjugate base concentration and acid concentration. So this is our conjugate base, right? And this is our acid right here. So at half of the equivalent, we have equal concentrations of those two forms. So if those concentrations are equal, then we have the ratio equal 1, right? Then pH equals to pKa. So it means that at half of the equivalents added, the pH on the y-axis should be equal to 2.3. And it's around here. So I'll just put that point right here. So when we add one equivalent, we deprotonate this acid completely. And now, if we start adding more equivalents of sodium hydroxide, we start already focusing on another equilibrium, which is the second dissociation reaction for glycine, right? That is characterized with the second pKa. And the same will be true here. So in this case, we will have the zwitterion form as our acid and fully deprotonated form as our conjugate base. So the same thing will happen. So if we reach that half point, which will be 1.5 equivalents of sodium hydroxide added from the beginning, we are reaching the point where pKa, pH is equal to the pKa, to the second pKa. So here we have that 9.6 point, right? So how we connect those points? Definitely, here we are dealing with a weak acid, right? So solutions of weak acids and weak bases are known as buffer solutions. And that means that they can keep their pH stable, right? But that happens within plus or minus 1 unit of pH with respect to the pKa. So we can say that, here, from, let's say, around 1.3 to 3.3, we have a very low slope of that curve, right? But outside of that, the slope is relatively, pretty high, right? The same is true about the second pKa. So here, between 8.6 and 9.6, we have a slope that is about 0, right? And now we are connecting those things, right? So I should probably start it. So we have something like that. That's a titration curve for glycine. Okay, so here another implication that you can discuss is that, we can actually go ahead and put here the charges. So we start with 1 plus, and at some point we are having the charge of 0, right? And then minus 1. So the neutral form, the zwitterion in this case, form of glycine, will be the most predominant maximal amount of that if we have a pH that is an average between those two pKa's. And that is referred to as PI, isoelectric point, the point or pH at which the predominant form of a molecule is this neutral, in this particular case, zwitterionic form of glycine. So that will be pKa of the carboxyl group plus pKa of the amino group by 2, right? And if we plug those numbers, I'm going to use a different marker to make it a little bit better here. And for glycine, it would be 2.3 plus 9.6 over 2, which is around 6, right? So 11.9, right? So we'll say around 6. So we can say that right here is our PI, right? So this is our PI, and not surprisingly, it exactly corresponds to the neutral form of glycine.